Welcome. Today we are solving LeetCode problem 49, group anagrams. Here is the problem. You are given an array of strings. Your job is to group the anagrams together and return them in any order. But first, what is an anagram? An anagram is a word formed by rearranging the letters of another word. For example, eat, tea, and ate are all anagrams of each other. They all use the same letters, just in a different order. Now, let's look at the constraints. The array can have up to 10,000 strings. Each string can be up to 100 characters long. And every string contains only lowercase English letters. Simple enough. In the next part, we will walk through a concrete example to make this crystal clear. Let's walk through example 1 to understand what we need to do. Our input is this array of strings: eat, tea, tan, ate, gnat, and bat. Now, we need to group the strings that are anagrams of each other. Group 1 contains eat, tea, and ate. All three share the same letters A, E, and T. Group 2 contains tan and gnat. Both share the letters A, N, and T. Group 3 contains only bat. It uses the letters A, B, and T, which don't match any other word. So our output is 3 separate groups. The key insight here is simple. 2 strings are anagrams if they contain the exact same characters with the same frequency. That is the rule we will use to group them. Now, let's look at 2 edge cases. Example 2. The input is an array with a single empty string. Since there's only one string and it has no characters, it forms its own group. So the output is a list containing one group, with just the empty string inside. Example 3. The input is an array with just the string A. Again, there is only one string, so it forms its own group. The output is a list containing one group, with just A inside. These edge cases teach us something important. Every string, no matter how short or empty, must be placed in a group. Our solution needs to handle these cases correctly. Now, let's think about the brute force approach. The key idea is this. If we sort the characters of any string alphabetically, all anagrams will produce the exact same sorted result. For example, eat, tea, and ate all become AT after sorting. So we can use that sorted string as a key to group them together. Here are the steps. Step 1. Create an empty dictionary to store our groups. Step 2. For each string in the input, sort its characters alphabetically. Step 3. Use that sorted string as the dictionary key. Step 4. Append the original string to the list stored at that key. Step 5. Once we process all strings, return all the dictionary values as our result. Look at the example at the bottom. Eat sorts to. Tea also sorts to. So they go into the same group. Tan sorts to ant. A different key, so a different group. Simple and effective. Let's now look at the actual code. Here is the brute force Python implementation. We define a function called group anagrams that takes SDRS as input. First, we create an empty dictionary called groups. This will hold our grouped results. Then we loop through every string S in SDRS. For each string, we sort its characters and convert the result to a tuple. We call this the key. We use a tuple because tuples are hashable, meaning they can be used as dictionary keys, but plain lists cannot. Next, if the key is not already in the dictionary, we create a new empty list for it. Then we append the original string S to the list at that key. Finally, after processing all strings, we return all the dictionary values as a list of groups. This is clean, simple, and works correctly. Now, let's analyze the time and space complexity. Let's analyze the complexity of our brute force solution. Time complexity, big O of n times k log k. Here, n is the number of strings in the array, and k is the length of the longest string. For each string, we sort its characters, which costs k log k. We do this for all n strings. So the total time is n times k log k. Space complexity, big O of n times k. We store all n strings in the dictionary. Each string can have up to k characters. So the total space used grows with n times k. Now, what is the bottleneck here? It is the sorting step. Every time we process a string, we sort it. Sorting is not free. Can we do better? Can we group anagrams without sorting at all? Yes, we can. That is exactly what the optimal approach will show us. Now, let's look at the optimal approach. The key idea is this. Instead of sorting each string, we count the frequency of each character. Since there are only 26 lowercase English letters, we create an array of 26 integers, one slot for each letter. Two strings that are anagrams will always produce the exact same count array. So we use that count array as the dictionary key. Here are the steps. Step 1. Create an empty dictionary to store groups. Step 2. For each string, build a count array of 26 integers. Each position represents a letter from A to Z. Step 3. Convert the count array to a tuple and use it as the dictionary key. We use a tuple because, just like before, tuples are hashable. Step 4. Append the original string to the list at that key. Step 5. Return all dictionary values as the result. Look at the example. Eat and T both give us the same count, equals 1, E equals 1, T equals 1. So they produce the same key and land in the same group. This avoids sorting entirely. Let's look at the code next. Here is the optimal Python implementation. We define group anagrams and start with an empty dictionary called groups. For each string S, we create a count array of 26 zeros, one position for each letter from A to Z. Then for every character C in the string, we find its position using ord of C minus ord of A. This gives us a number from 0 to 25. We increment that position in the count array. Once we have the full count, we convert it to a tuple. This makes it hashable, so we can use it as a dictionary key. Then, just like before, if the key is not in the dictionary, we create an empty list, and we append the original string to that list. Finally, we return all dictionary values. The key difference from brute force is this: instead of sorting, we count. Counting each character costs linear time. There is no log factor. This is faster for long strings. Let's analyze the complexity of the optimal solution. Time complexity. Big O of n times k. N is the number of strings, and k is the length of the longest string. For each string, we count its characters, which costs k. We do this for all n strings. There is no sorting, so there is no log factor. Total time is n times k. Space complexity. Big O of n times k. The space usage is the same as the brute force. We still store all n strings in the dictionary, and each string has up to k characters. So, why is this better? Look at the comparison at the bottom. The brute force runs in big O of n times k log k because sorting each string adds a log k factor. The optimal runs in big O of n times k. Counting is always linear, so we remove that log k entirely. For long strings, this is a meaningful improvement. And in coding interviews, removing that log factor is exactly what interviewers look for. Let's connect the two approaches and understand how one leads to the other. The brute force sorts each string and uses the sorted result as a dictionary key. The insight is correct. Anagrams always sort to the same string. But sorting costs k log k per string. That is the bottleneck. So we asked, can we find the same grouping key without sorting? The optimal approach answers yes. Instead of sorting, we count the frequency of each character. Two anagrams always have identical character counts. So we use the count tuple as the key instead. The rest of the code is completely identical. Same dictionary, same grouping logic, same return statement. The only thing that changed is how we compute the key from a sorted string to a count tuple. That single change removes the log k factor and gives us a faster solution. That is the power of thinking about what information you actually need and finding a cheaper way to get it. Let's wrap up with a side-by-side comparison of both approaches. The brute force sorts each string and uses the sorted string as the dictionary key. Time complexity is big O of n times k log k. It works, but sorting adds an unnecessary cost. The optimal approach counts each string's characters and uses the count array as the key. Time complexity is big O of n times k, no sorting, no log factor. Space complexity is the same for both, big O of n times k. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.